Okay, so this is a pretty long example. I'm not going to read it to you. I know you can read it yourself. So if you need to, go ahead and pause the video so you can read up this scenario. All right, I can wait. Go ahead, read it. All right, so basically what we're trying to figure out is down here, for what speed can the calculus cop B ticket the farmer? All right, so if we talk about the mean value theorem, it kind of says the instantaneous velocity somewhere has to equal the average velocity. So what was his average velocity over this trip? Well, he went 5 miles over 4 minutes, and 4 minutes in hours would be 1/15 minutes. All right. So if we divide that, the average velocity was 75 miles per hour. So the cop, if the calculus is a smart cop, I mean, if the calculus cop is a smart cop, then somewhere his instantaneous velocity had to equal his average velocity. All right, but remember that the mean value theorem only applies if the function is continuous and differentiable. All right, continuous on the closed interval and differentiable on the open interval. So I want you to decide whether the function is continuous or different or differentiable. All right, so as the guy drives from part A to part B, would his trip have to be continuous? Would it have to be differentiable? Is there any way that his graph could look like this? All right, or could his graph look like this, where there's a hole? All right, this is something that I want you to write in your whisk. Okay, don't forget to put that in there. Is the function continuous of the guy driving from one point to the other past the cops? And is the function differentiable? Is there any way that it could look like any of the ways that it's not differentiable? All right. And then just comment, would this ticket hold up in a court of law? And let me know why you think that. So this is something that you need to do right in your whisk. All right. The next problem, let f of x be a function that's differentiable for all x. So how large can f of 2 possibly be? All right, so this happens to be in the mean value theorem section of our notes. So there's a good chance we might have to use that. All right, so we want f prime of x. We want that derivative at a point to be equal to the function value. Oops, that's a 2. At that point, I mean the slope, the average slope, the slope of the secant line. All right, 2 minus 0. So we just need to figure this out. F prime of x is less than or equal to 5. Not what I meant to write. There we go. All right. So this whole thing, the derivative, has to be less than or equal to 5. So this part also has to be less than or equal to 5. All right, f of 2, we don't know what that is. We're trying to figure that out. Minus f of 0, which is negative 3, over 2 minus 0, which is just 2. All right, so 5 is less than or equal to f of 2 plus 3 over 2. Okay, we can multiply both sides by 2. And we could subtract 3. So then we just figured out that f of 2 has to be less than or equal to 7. All right, so that was part A. Using that same kind of idea, f prime of x has to be greater than or equal to 3. So then that average rate of change, there we go, that I couldn't think of that earlier, f of 5 minus f of 1, that average rate of change has to be also greater than or equal to negative 3. All right, so f of 5 is 2. F of 1, we don't know. We're trying to figure that out. Over 4 has to be greater than or equal to negative 3. And this is part B, by the way. So then 2 minus f of 1 is greater than or equal to negative 12. All right, so I can move the negative 12 over, and I can move the f of 1 over, so I get 2 plus 12, which is 14, and that has to be greater than or equal to 1. So my function has to be f of 1, the largest possible value has to be less than or equal to 14. All right, and this is where we're going. All right, this is the big deal here. So we've had two different functions before. Let's say like f of x equals x squared plus 4. All right, and g of x equals x squared minus 17,000. Why not? All right, the derivative of this one would be 2x. The derivative of this one would also be 2x. So these functions above, remember, they only differed by a constant. All right, so this is where we're going. We're almost here, but not quite yet. We have to practice a little bit more. So we're trying to find the function whose derivative is sine of x. All right, so we could call the derivative sine of x. All right, and whose graph passes through this point. So if we plug in 0 to our function, it had better equal 2. All right, so the going backwards, can you figure out what we would have to take the derivative of to get sine of x? And hopefully you do know that it could be negative cosine of x, right? It could be that. This is called anti-differentiation. It's the antiderivative. And we will get into that a little bit later this year, but it's just a basic idea. It could be that, right? Or it could be plus 1, or it could be plus 2, or 10, or 1,000, all right? We don't know. So we have to put plus some constant value. But we know that f of 0 equals 2. So if we plug this in, plus c, it has to equal 2. Cosine of 0 is 1. So negative 1 plus c equals 2. And c would have to be 3. So the function, exactly that one, all right, that fits both of these different conditions would have to be this function. All right, so this was a pretty short video today, so that means that you're going to spend quite a bit of time working on your worksheet.